So, welcome everyone. It is my pleasure to basically present you Dr. Fermín Mallor. Fermín has been a student of this university, has pursued his bachelor thesis in aerospace engineering here at UC3M with us. We had the chance to collaborate with him in several papers actually. And then he moved. Yeah, we still have one pending actually. And then he moved to KTH for his master thesis and for his PhD in engineering mechanics with a specialization in fluid mechanics. Now he transitioned to industry in predictive IQ, but I will leave him to present by himself the company. So thank you.
Yes, thanks a lot. So basically, I'm here to present what we do in my company, which is PredictiveIQ. And what we do is bring the physics and artificial intelligence together for the purpose of industrial innovation. And what we do essentially is accelerating engineering and also optimizing product and process performances. So, se murió esto. So just a brief overview of the talk in general. I will start with just a short bio about myself and also presenting the core team behind PredictiveIQ. Then I will move on to briefly explain the technology that we work with, which is essentially small data, physics-informed artificial intelligence modeling, and present our capabilities and solutions. Then I will go through one case study where I will just explain a specific case from the accelerating engineering part. Of course, I had to redact a lot of specific information, but I think it shows a picture of essentially what we are able to do now. And then lastly, I will end up with some opportunities that we have now open and will be open at PredictiveIQ, and also leave my contact in case you are interested. So let's start with a short bio. Essentially, as Marco said, I started my higher education here at UC3M, doing aerospace engineering. But I also started doing research here with professors Andrea Llanero and Stefano Dicetti, who are back there, and I guess you all know them. And with them, we did some pretty cool experiments on turbulent heat transfer, which got me started in, let's say, the academic and research world. Then after that, and following professors Llanero and Dicetti's advice, I moved to KTH to pursue a master's degree in engineering mechanics, specialized in fluid mechanics. And there I got into contact with Ricardo Vinuesa, Philip Slater, and Rami Sorlu. And since the master, I started doing research with them. Then after I finished the master, I transitioned into doing a PhD with them as well. And the PhD essentially was about studying turbulent flows around wings, and more specifically about turbulent boundary layers and how they separate when you go at high angles of attack. Apart from that, when I finished the PhD half a year ago, I also did some research on artificial intelligence, specifically large language models and their application to sustainability policies. And then since the last couple of months, I've also been a part of the PredictiveIQ team. And essentially here I have two different positions. One is Director of Growth, where I'm tasked with expanding the commercial operations within the European market. And the other part is being a Product Manager. So essentially, I also lead engagements with our commercial partners. Then a bit about the PredictiveIQ team. This is a very strong team with very experienced professionals coming from both academia, but also industry. The core team essentially is made up of 4 people. One is myself, so I don't need to introduce myself. But just for you to know, I'm more in the commercial side of the business. Then we have Juan Fernando Betts, who is the CEO. He got his PhD in aeroacoustics from Virginia Tech, also collaborated with NASA. And he has an MBA from MIT and more than 25 years of experience as an executive. Then we have Ahmad Peyvan, who also holds a PhD, and he's a senior researcher at the Crunchy Group in Brown University under Professor George Karnedakis. Ahmad Roshdi, who is a senior manager of research and collaborations in Stanford University's Human Centered Artificial Intelligence. So essentially, he's at the forefront of all the advances in artificial intelligence, large language models, and so on. And he deals more with the part about defense contracts. Then we also have a pretty strong board of advisors, comprising of Professor George Karnelakis from Brown University, who is the mastermind behind physics-informed neural networks, depot nets, and a lot of advances in this area of merging physics with artificial intelligence. Then Associate Professor Ricardo Minuesa from KTH, who has a very strong track record of using AI for fluid mechanics and sustainability. And then Mr. Joao Perez, who was an executive at IBM and has a lot of experience leading his own companies to success. So that's it for the team. And now let me get a bit into more details that might be interesting to you, which is the technology and the solutions and capabilities that we have. So essentially, the company, this startup, comes from the fact that we spotted a mismatch between traditional artificial intelligence / machine learning methods and the industry needs and requirements. So the way industrial design and operation works right now is in a way that they have several challenges. When you're trying to design a new product, especially in an industrial capacity, let's talk about automotive, cooling, aerospace, all of these sectors, you really need to run very costly simulations of your prototypes. Simulations that may take days to run and are expensive financially. Also, these simulations are this whole process of creating your prototypes and simulating them is very manual, and there is little automation. There is now a big push into automating and harmonizing all of these processes, but we are still far from being able to automate this. The other problem is that you have a large number of design parameters and a lot of stakeholders putting their own constraints and thoughts into design. So it's not only about performance, but it's also the style of the product. There are many things that manufacturability. So there's many things that come when you come to the design, and this all ends up leading to under-optimized products, right? And very long horizons of time to market for new prototypes and designs. If you look at traditional, or let's say big data, artificial intelligence, machine learning approaches, the problem that they have when they try to deal with these problems is that they're extremely data hungry. And that is in direct contrast with the first point, right? If you have very expensive simulations, you cannot have thousands of them in order to train a model. The other problem is that they very quickly diverge when you go outside your training distribution. And if you have many parameters and a very low number of simulations available or independent data points, it's quite hard to get those spaces just right in order to have good predictions. And also, it's if you just use, let's say, a neural network, it's very hard to encode design parameters and obtain fully 3D results robustly. So there is clearly a mismatch here, which we spotted, and the way that we solved it and our value proposition is to use generalized physics-informed AI for these kind of industrial applications. So what is generalized physics-informed AI? So the first part is it is generalized. We use novel architectures that go away from traditional neural networks, and we go more towards kind of operator neural networks. This enables much better interpolation, but also your extrapolation is not as bad. Let's say we are able to generalize much better. We don't diverge as soon as we get a little bit outside from your training distribution. And that is very important for model robustness and stability. The other part is that these models are extremely data efficient. So physics, by introducing physics, the known physics of the problem into your models, you're able to have a higher predictive accuracy while using very little data. And the last part, which brings this whole thing into actual engineering, is that you can make these solutions, these kind of component systems, into a modular components, and then kind of put them into a model-based system engineering framework. And then you are able to model entire systems and create digital twins. So this is a bit of kind of the roadmap. Traditionally, right now, big companies are stuck here, let's say, just doing CFD simulations. But in the last years, there's been a lot of push to try to leverage machine learning methods or data-driven methods in order to create what is called reduced order models, right? In order to avoid having to run so many simulations and try to explore a bit better the parameter space that you have. They give you fast predictions, but their accuracy and generalizability is not the best. Then, as I mentioned, kind of like 5 to 6 years ago, physics-informed neural networks came to be. And what they do is essentially you have your normal neural network, but then since you know the physics of your problem, you can impose those into the neural network. And you can do that in a couple of different ways. Let's say you can do that weakly, where you impose the residual from your equations into the loss term. So you are kind of weakly imposing the physics of the problem, or you can actually build the physics into the architectures by using things like Laplacian neural operators and so on. And then the last bit here is the neural operators, where we go from traditional kind of single input space neural networks to learning operators. So we approximate operators instead of functions. And then there is much more stuff that we use, obviously. So then you don't need to have only neural operators. You can have physics-informed neural operators. You can have multi-fidelity physics-informed neural operators, transformers, geometry encoder decoders. Now we are getting a lot into generative AI as well. So there's many other things, but the basis is going from this point to the physics-informed neural operators. So a bit for those of you that don't know what a neural operator is, the most famous one is the DeepNet, the deep neural operators. Also, the FNOs are quite famous. And essentially, this DeepNet is based on the classical universal approximator theorem. But here, instead of trying to approximate functions, we try to approximate operators. An operator G, which is dependent on two things. On an input function, so you can input functions into your neural network, and that is being done into the branch part of the network, and then the points where you are going to sample your output function, which is the input to your trunk neural network. And this gives much better results than trying to directly use a normal neural network. The other thing that we leverage quite a lot is the concept of transfer learning, which essentially this allows you to kind of pre-train, pre-build your models, right? And then when you deploy them, you typically will deploy them on edge platforms or cloud platforms, and you want those to be very nimble with very little computation, but still adaptable, right? And the way you do that is by leveraging those pre-trained models, fixing most of the parameters, and just adapting some of them to the new observations that you have. And in that way, you can continuously learn without having to continuously retrain the model from scratch. And this is, unfortunately, I cannot tell the case where this is coming from, but this is just to show kind of the power of this new paradigm. So here we compare two approaches, one traditional neural network and our small data AI, for a case where we wanted to do predictive maintenance of a kind of thermal fatigue predictive maintenance case. This is a very complex case, and as you can see, when you input physics and you use novel architectures, just with 3 independent data points, you are able to predict extremely well the case, right? On the other hand, if you use a traditional neural network, right, you can see here the massive scatter in your data. So, and this is kind of where value is being added. Very little data gives you very good results. So what are we doing with this technology? Well, we have 2 different parts. The first part is what we call accelerated engineering, where, as I mentioned before, typically you would need to do a lot of CFD or FEA calculations on new products. They are very expensive. And using this small data AI, what we do is create surrogate models that allow you to go to optimize much better your products, explore much better your parameter space, doing sensitivity analysis and so on, and also really accelerate your time to market. And for example, one of our flagship cases is with Scania, where we are doing the optimization of the whole cabin of their new truck models. And then this links pretty well with the second part, which is optimized performance. So because we have this kind of small and very data efficient surrogate models that give predictions almost instantaneously, we can actually embed these solutions either on cloud or on edge, so while the product is operating. And this allows us to get very good predictions of, let's say, product possible failures or maintenance needs. And this allows companies to optimize their whole supply chains, maintenance schedules, and operations in general. So essentially what we offer here is a complete solution lifecycle, right? From the accelerated engineering point, we accelerate the 3D simulations that are needed to create the products. Those simulations are modular. Like once we have the surrogate models, we can modularize them and introduce them into a model-based system engineering to create fast and accurate system-level optimization. So we can, let's say, optimize and simulate very accurately and fast whole systems. Then, once this system model has been created, you can enhance your product performance once it's online. And this enhanced product performance, together with the high accuracy of the predictions, allows you to optimize holistically your whole supply chain, maintenance, and repair operations. So we have already quite some traction within the commercial space. So we are a startup, but the company has been running for a couple of years now, and we already have established clients and products. For example, here with Munters. Munters is an HVAC and cooling company, mainly. They have a lot of different products, but we are working here with their data center division. And we created some surrogate models for them in order to optimize some of their data center cooling devices. And I will explain this case in a bit more detail later. And then for Scania, as I explained before, they are coming up with their new trucks, and they wanted us to optimize the truck cabin shape. And they only provided us with 90 simulations of different concepts that they have. And with those, we create this surrogate model and tell them like which parts specifically of the truck are most important for drag and how they should be. Maybe they don't use the exact geometry we give them, but all the insights that you can gain from these surrogate models are extremely important for them, because then they can go and talk with the other stakeholders in the design process, like the style design, industrial design, manufacturers, and so on, and come to a compromise on the parts that are most relevant for, in this case, drag reduction. Then the other part that we have, and which is actually, if you look at it, is the biggest market, is the optimized performance market. And optimized performance, in the end, is all about creating digital twins of products. In this case, we work very heavily with the Department of Defense of the United States. Our technology was actually selected among 100 companies as a strategic technology for the XM30 fighting vehicle program, which is right now is the biggest military contract in the world. And our solutions are being embedded into, for example, the engine part, where we do predictive maintenance for certain engine parts, and also overall for all of the other systems within the XM30. Now, I will go on to a brief case study. As I mentioned, this was work done for Munters, and our task was to essentially redesign the coils that are in the evaporator and condenser of Munters C-School system, which is a system used for data center cooling. Here you can see the whole system. Right? You have your data center. You need to dissipate a lot of heat because they create a lot of heat. And the way you do that is by running coolants through these coils, right? And this coolant goes from liquid to gas, and then you dissipate the heat to the outside. The problem is that due to the new regulations by the European Union, the coolants that were used everywhere have been banned, and they need to be replaced with more eco-friendly coolants. which is great for the environment, but the problem is that they are 15% less efficient. And of course, this is a massive problem where you have data centers that are not going to decrease their load by 15%. If anything, they're just going to increase their heat load, right? So Montes came to us with the task of redesigning the coils that are in the evaporator system. And essentially, we needed to optimize them. And this is a very complex case because you have a liquid that is getting transformed into gas, right, through these ducts. Also, the coils itself are quite, let's say, have a lot of parameters. It's a list right here, but essentially you have parameters like the number of holes they have, the height, width, and also another thing that Montes wanted to explore is whether adding protrusions into the coils themselves would help with the heat transfer. So we are talking about essentially just generalizing the whole geometry of this coil design and being able to, in this very large list of parameters, find the optimal design. And not only that, they also wanted to know which of those parameters were most critical for their design. And essentially what we need to do here is increase the efficiency. Their task was to just get back to the efficiency they had before. So we had to get a 15% increase from the baseline right now. And that means reducing the outlet air temperature in the evaporator. So you want the air coming out from the system to be cooler, and also reduce the outlet refrigerant temperature in the condenser. And the problem here is that there were quite some manufacturability constraints that also need to be embedded into the whole optimization. So how was the workflow here? Well, the first part was with exploring the problem with a low fidelity model, which is the industry standard, but which allows you to essentially change some geometrical parameters, and with kind of 1D simulations, you can get an approximate performance of your system. But by doing that, we saw that there was just a 5% heat transfer gain. So then we went to the next step, which was parameterizing the whole geometry, identifying critical parameters, and knowing how to vary them within the constraints. And then we use a low fidelity model in order to get the boundary conditions, initial conditions for the high fidelity model, because now we wanted to do the whole thing in 3D to be very accurate for them. And then once we establish our kind of 3D CFD simulations, we run a total of 150 of them, 100 for training, 50 for test and validation. Then we train a DeepNet model from which we optimize the geometry and also did a bunch of sensitivity analysis studies. So this is the high fidelity workflow, so how the CFD works. This is an extremely complex case, but as I mentioned before, there is a pre-processing part where you need to actually create your geometry based on whatever design parameters you have there, measure the geometry, and also use this low fidelity system in order to get some initial parameters. Then you do some steady state simulations where essentially you do a RANS, a Reynolds average Navier-Stokes simulation of the system, assuming everything is liquid in there. And this gives you about the initial conditions to carry out your unsteady simulations here. These unsteady simulations are quite complex because they involve an evaporative process. And once you have it, you can get out the heat flux and the pressure drop, which are the two critical parameters. So the heat flux needs to be maximized, but the pressure drop needs to be contained within a maximum allowable pressure drop, because then if you increase pressure drop too much, then the operation of the system becomes very expensive. And this is just a bit of how the flow field look. So essentially what we get out is the thermal conductivity, temperature, and pressure. And from these things, we can get the heat transfer and the pressure drop. With that, we use these simulations, the data from them, in order to train a DeepNet model here. And as I mentioned before, what we did is that we have a branch network which encodes the input function. In this case, the input function is all of the geometrical parameters. And then you have the trunk network, which is the whole 3D mesh, essentially, all the points where you actually want to predict. And the beauty of this is that these points, you can put whatever you want and you can predict all around, right? You are not fixed to a set of points as you would in a normal neural network. And then we would get the same parameters as in the CFD simulations, and then with post-processing you get the heat flux and the pressure drop. So now here, I will show you just some of the results. Here you can see how the heat flux changes as we change the geometry of these coils. On the left, the predictions from our model, and on the right, the CFD results. And as you can see, the correlation between both is very good. So we are able to get very accurate precisions with just 100 simulations. And actually then we tested, and probably with way less, we would have gotten these predictions as well. So once your machine learning surrogate is trained, and because it's dependent on that branch network where you have all of your input parameters, we perform a complete sensitivity analysis of all the parameters, as well as a constraint optimization. And this part is quite important, especially the sensitivity analysis, because, for example, here, Mantes was constrained by the manufacturability abilities of their supplier, right? But if you identify that maybe being able to make a fillet smaller or decreasing some radius would have a very high performance, you can actually quantify in terms of money exactly what is the gain from it, right? And then you go to your manufacturer or other suppliers, and you can ask how much adding that kind of new degree of manufacturability would cost. So you can get an ROI directly, right? So you know your return on investment, and you can make informed decisions on your new products, on your suppliers. So the ability of doing this sensitivity analysis is actually something that is not more important, but as important as just getting the optimized shape. And essentially our results when we did this redesign was that we were able to get over a 40% increase in heat transfer while being below the maximum allowed pressure drop, right? Mantes just wanted 15%, but by using this kind of advanced method, you can actually get something that is much higher. And actually the surprise is that when we were doing the low fidelity, which is what they did before, our estimation was that maybe we could get 5 to 15%, if anything. So this was quite surprising. And actually, even without adding protrusions, so by just optimizing the geometry, we were able to get close to a 30% improvement and reducing the pressure drop. So this is already way more efficient than what they had, and would work even better with the new coolant than their current system at a lower operating cost. And now, just to conclude, I would have liked to present a bit more, stuff that we've done, but there is an industrial secret, so cannot really do that. But now we are growing quite a bit, and we have a bunch of opportunities. We have opportunities for full-time positions, collaborations with academic members, and also for students some internships like master thesis or PhD stays and so on. Right now we already have 2 full-time position openings, but they are in the US. But we expect for the Q1 in 2025 to open probably another 2 more in the US and 2 to 3 more in Europe as well, in case anyone is interested. And then there is also the possibility of doing master's thesis or doctoral stays. We are actually going to join a doctoral network soon. So those things are also possibilities in case anyone wants a stay in a company that is very close to academia, but actually working on industrial cases. And then just to mention that we have a very strong track record of collaboration with universities, with Brown, Stanford, KTH, and MIT as well. And then here is a list of possible topics that we would be interested in exploring. Although, this is just a list that I came up with, but it could be anything. We are very open for suggestion. So, for example, development of multi-fidelity, multi-physics models. One option with this would be to do aeroacoustic simulations without having to actually run the whole aeroacoustic simulation, which is very expensive. So trying and then putting that into a multi-fidelity framework to do things separately and then get the overall result. Then something that we are extremely interested in is the development of a generalized geometry parameterization using, for example, autoencoders. And also, when it comes to system simulations, instead of just using Modelica or some of these system simulations, we are also exploring the use of AI surrogates, probably based on deep reinforcement learning, in order to substitute and create a surrogate of the whole system. But we are, as I mentioned before, we're very open to suggestions or any other possible collaboration pathways that you may think of. And yeah, with that, I will just want to thank you for your time. And this, if you scan it, you can connect on me on LinkedIn in case you want to contact me later. But if not today, I will be here, probably Monday as well. So if anyone is interested in collaborations, in exploring any opportunities, just if you see me around here, just talk to me. And thank you.
Well, thanks, Fermín. Okay, so thanks, Fermín, for this nice talk. Sure that the audience is plenty of questions. I can see Mario already there.
So Fermín, very nice to see you, and thank you for the talk. I was wondering about the case that we're showing with the cooling and the protrusions and so on. What did you use exactly to train your network? You were using the high fidelity simulations?
Exactly, we use the high fidelity
Right.
CFD. I mean, it's high fidelity. It's not like an LES or something. It's a RANS, but that's
Okay,
as
well,
high fidelity
good
as
enough.
you get.
But you also use the equations for the the fluid equations and the heat transfer equations somehow,
was,
right?
That was embedded.
Okay. All right. So how do you input them exactly? You input them as part of the loss?
In this case, they were as part of the loss.
Okay.
Yeah.
Okay. All right.
Yeah. But I mean, there are ways of putting them like as a hard constraint into the model as well.
Okay. I guess that the real question is, it took you like 100 simulations for the high fidelity code to reach the conclusion that this was the optimal geometry and so on. If I were to use only this tool, the high fidelity CFD simulations, could I reach this conclusion in the same number of simulations as you?
If you use
or conversely, can you lower the number of high fidelity simulations that you need to train your model to the same degree of accuracy?
Yeah, that's the thing. I mean, we went too overboard with the CFD. Probably half of them would have sufficed for a similar level of accuracy. And the thing is, since you have so many parameters, right? Let's say you have 10 different parameters that you can vary in a range. The number of variations, like in that kind of hypercube, that you will need to explore to get even close running CFD simulations, it's very large, right? There are different ways of doing it. Like you could probably put everything into like a Bayesian framework to try to kind of optimize which simulations you're doing and so on. But that would still not give you like a complete kind of smooth picture of the influence of your parameters.
Can you even go to the limit where you use no CFD simulations at all? The physics are already in the equation, so...
Yeah, I mean, this is something that Professor Karnevakis is exploring, but still you always need to couple with a physics solver for your initial parameters and so on. So, I mean, once you have like some good initial solution, you can do that actually. And the thing is that because when you do these machine learning models, you are always saving the gradients. You can compute the equations much quicker than with a solver. But you cannot go from anything to having things working right.
Okay, any other question?
Hi, thank you for your talk. I just wanted to ask you about the opportunities.
Yeah.
You talk about the full-time positions and collaboration opportunities, but what about internships? For instance, if we are studying a master, could we do an internship with you to learn more or to stay a few months?
I think that can be set up actually. Yes.
So just on request, no? So we can just contact you.
Yeah. Exactly. I mean, right now we're setting up the European entity, which is to have like a legal entity in Europe, but that should be done by the end of this month, should be operational already. Once that is done, so the whole process becomes way smoother to do it. Yeah.
Thank you very much.
Yeah, no problem.
Okay, some other questions from the audience? Well, just one question which perhaps may be interesting for everyone here. So you indeed come from a background which is mostly fluid mechanics, but indeed your company is working on several problems. So when you are looking for positions for openings in your company, do you have a specific, let's say, profile you're looking for, or?
I mean, we like to get people that know about physics, obviously, a bit. I guess everyone here does. So that is the first filter you have already passed. Then also, it's not, I mean, yeah, if you know how to program, great. That is like, basically it's necessary for the kind of stuff that we need. But there are different parts, right, within the stuff that we do. So we don't need everyone to be just programming AI. So like to know just PyTorch and just programming just the AI model. There is so many other things, right? For example, like doing morphing of geometries is, or this what I mentioned, like creating generalized parametrizations for very complex geometries. There's a lot of other things. It's not only fluids, it's not only the simulations part. There is a lot about just pure engineering, pure connecting things together.
Okay, thank you, Fermín. So if there are no more questions from the audience, I think we can close this seminar here. So I wish to thanks Fermín again. So a round of applause.